Okay, hi and welcome to Video Notes 8.7 Exponential Functions. In this section, we're going to explore exponential functions, which can be difficult to understand because of how they grow. So what we're going to do is we're going to try to look at a function that we know already, linear functions. We're pretty comfortable with them. We know that they have a constant rate of change. So to do that, I'm going to ask you to look at these two tables on your screen. You've got two tables here. You've got one table, two tables. And in those tables, you're going to be able to see one's linear and one's exponential. So I want you to do that. I'm going to pause the video here in a second. And then I want you to think about when you decide which one's growing linear and which one, or at a constant rate of change, and which one's growing exponential. I want you to decide how you know that. And I want you to write that down. Then we'll meet back here. Okay, welcome back. What you should have found then is the one here on the left, we would say is a linear function. And you would know that because it's kind of growing at a constant rate. How do you know that? Well, if you look down the list, 3 to 6, 6 to 9, 9 to 12, 12 to 15, 15 to 18, it seems to be growing by the same amount each time, which is 3. If you look at the list on the right, which we'll say is exponential, it seems to be growing faster each time that we do this. And each one, if you'll notice at the bottom of the table, is growing immediately faster, where if you look at the linear table, we start at 3, we end at 30. It grew a little bit. Okay. If you look at the exponential, it grows from 3 to 9 to 27, so it's a multiplication of 3 between each one. You should have been able to see that. But look how big it gets by the end, substantially bigger. Now, we can use this growth in these tables, looking at how it changes over the y intervals, by finding what we would call differences. Now, we can use differences to verify that a function is either linear or exponential. Here's how you do it for a linear function, which we've done in the past. For a linear function, we compare the y values, usually in this order, y2 minus y1, and so on and so forth. y3 minus y2, you get the idea. So we take the second point minus the first one, 6 minus 3, 3. In this case, we would take 9 minus 6, 3. And you should be able to see that this pattern all the way through the table is the same, or constant. That's why we use that term constant rate of change. If these are constant all the way through the table, it means that it's a linear function. That's what that means, if you can verify that. Okay, again, one thing we forgot to mention here is that these values on the x need to be consecutive or move by 1. Otherwise, we need to account for that. Okay. And when we look at the exponential, we have a similar way to identify if a table of values is an exponential function. So let's take a look at that. In this one, when we find its difference, we're not going to find a constant rate of change, which we've talked about a few times here for the linears. We're going to find what we call a common ratio. Now the common ratio is done a little bit different. Instead of subtraction, because these are adding up, these are multiplying up by 3, it's going to be a division of the values. So what we're going to do is we're going to compare the two, but in this case we're going to take y2 and divide it by y1. Okay? That's why we call it a ratio versus a difference where we do with linear. So if we can find the same thing, that these are constant all the way down, then that means that this is a exponential function. So 9 divided by 3, 3. 27 divided by 9, 3. 81 divided by 27, 3. And you get the idea. It will be the same all the way down. If these are constant, then we call this an exponential function. That's how we look at a table of values to identify if it's exponential. Okay, so now that we know that linear functions have a constant rate of change and exponential functions have a common ratio, and we can identify those in a table of values, checking the y values, let's take a look at the base form of what an exponential function is. Not the parent function, but a base form of it. It'll look something like this. So y equals, indicate that it's a function. You're going to have an a value or something multiplied here in the front. And what we like to refer to that as an initial amount. Okay, that can be lots of different things. Money, product, animals, bacteria, populations, people, lots of different things. It's the initial amount of whatever we're looking at that's growing, or we'll find out later, or decaying, exponential decay. The next value that we'll find is our growth factor. probably the most important part of the exponential function. How big is it getting? What is it growing by? Is it 100%, 200%, 300%, half? It can be a decimal. So we'll explore that as well. And then the x, or a variable in this situation, is an exponent. That's unusual for us. In this position, x, just like normally, is your independent variable. Time periods, changes, events, things that occur in this growing. And so we've listed those out. Now, it's difficult to really understand kind of that exponential growth. So let's take a look at a quick little video here that'll maybe help us see a better, or get a better understanding of this.
Now we can see for ourselves what exponential growth looks like by doing a little experiment. And if we can bring one of the handheld cameras in, we can have a look at this. So in this box, I have 225 armed mouse traps. And on each mouse trap, we have a ping pong ball. Now in a moment, we're going to take one more ping pong ball and we're going to drop it in through this hole in the top. And it's going to set off a chain reaction. And in this chain reaction, the number of ping pong balls flying through the air is going to grow exponentially. Okay, so who would like to volunteer to come and set this off? My goodness. Let's have you there. Yep. Yes, you'd like to make your way along the end of the road. If you'd like to come and stand just there, and just turn that way. Okay, that's good. And what's your name?
Matthew.
Matthew, you'd like to hold that. Now, in a moment, we're going to give you a 3, 2, 1 countdown, okay? When we get to go, all I want you to do is to place the ball in through that little hole at the top. You manage that, yeah?
Yep. Okay.
Are we ready? 3, 2, 1, go! Amazing, excellent. Okay, thank you very much. Okay, so we have a high-speed camera that was looking at that, and perhaps we can just do a little action replay and see that in slow motion. So there's the first ball, setting off a couple more. Each of those is setting off several more. And on that curve, we can see the number of balls growing in this very dramatic way. But what's really impressive about exponential growth is that the rate of growth is itself growing exponentially.
Okay, so now what we're going to do is we're going to take a look at how the exponential function works with vertex form. You can see it over here. It looks like this. I can take a look at it there. By looking at this function, you'll notice that it's very similar to one that we know in absolute value. In absolute value, we learned vertex form. And with that, we knew that this h value and this k value was its vertex. You can see that we've labeled the exact same thing here. The h and k is the vertex of the function. And with an absolute value, that's pretty easy to identify. It looks like a V, so the vertex is in the center. And we said that when we moved h, if it was positive, it moved this vertex to the left, if it was positive. And if it was negative, the value inside the absolute value with h, if it was negative, it moved it to the right. And if there was a k value, it moved it up if it was positive and down if it was negative. It was pretty straightforward, but we were always talking about this vertex here. Well, with an exponential function, let's take a look at one. If we look over here, here's an exponential function. It doesn't have a vertex. And I can squeeze this down and we can look out farther and it just gets bigger and bigger. Let me put the projector mode on here. And it just gets bigger and bigger and rises and faster and it just almost looks like a straight turn if we scroll out far enough. So there is no real vertex for this, but you'll notice that there's a common point here. And if I zoom down to it, you'll notice I can highlight it there. For an exponential function, our vertex will be the point, or x coordinate 0 and the y coordinate 1. So 0, 1 will count for our vertex for an exponential function. So now that we understand where the vertex is, we can take a little bit closer look at the actual vertex form. It's not too different from what we already know. we can see that there's a value, h, that's applied to x. There's that same negative there that we're used to, right, that makes it opposite our directions. So we're going to find that if it's positive and there's a value added or subtracted to h, if it's positive, it's going to move it to the left. If it's negative, it's going to move it to the right. And we'll also find that k functions very much the same way. If k is positive, it'll go up, and if k is negative, it'll go down. So let's explore that a little bit farther. We're going to take the parent function 2 as our base and then raise it to the x power. And each time we talk about an exponential function, that exponential growth, or our b value, will change. So it's different for each function. So we're going to use 2 because it's a common exponential base. So with that common exponential base, let's take a little bit closer look then at how this works. So here I am in Desmos, and I've got it in a slider function. So this is a common base of 2. So let's take a look. If we look over on the side here, you'll notice that it's 2 raised to the x power, giving us a parent function of a growth factor of 2 and our x. And we can slide along here if we want, and we can see how, maybe I'll let me slide along here. You can see it there. You can slide along, and you can see the values change, and those y values get really big really fast. But we've got a slider built in here. And here it is. Here's our growth factor, b, raised to the power of x. And there's our vertex form, so there's a minus h. So this will shift it left and right, as we suspect, and this should shift it up and down for our k. So we can take this slider, and we can manipulate it and see what happens. So let's change a couple of these values and just play with it. So let's take h, which is at 0. So right now it's not there. Let's make it, I don't know, let's slide it to the right and make it a different value. And as you'll notice, I slide it to the right. Let's slide it to see if we can get it right on 3. There's close to 3. There's 3. So if we slide it over to the right on 3, what you should find out is that this value here is, there it goes, is 3 and 1. So if you take your vertex and we made h3, it means it moved it right 3 units, if I can hold it there. Okay, so it's 3 and 1. So if you take that x coordinate, shift it right 3 units, there you go, 3 and 1. So you can see all we did is shift it to the right. And if I play with the slider, and you guys can play with it too, all it does is shift that value to the right if it's a positive value. Okay, going in. So it'll look negative inside the function, don't forget. And if I make it negative, it's going to slide it to the left. So again, h, and you can see that this is the part we're manipulating, shifts it left and right. So let's go back and make that 0 so we can't see it for now. Okay. This is a lot harder than it looks. There we go. So now let's go ahead and take and move our k around. And as we suspect, as k gets positive, it should slide up. And you'll notice it doing the same thing. So let's put k on a value that we can predict. So let's put it on 4. So there's k on 4. So we just made this k value here, positive 4. And we already know our vertex was at 0, 1. So our y coordinate is 1, looking right here. And this point right here should be 5 because we went up 4. And again, k will work the same way, shifting it down. So you can see that vertex form works the same for exponential as it does for our absolute value. It's the same consistent movements. Let's throw in here, let's put these values back to something like they were. So I'm going to make h0, I'm going to make k0, and let's just take a quick peek with a, again, growth factor of 2 for our exponential function. Let's take a quick peek at what a linear function looks like when it's increasing. So let's expand this out just a bit. You can see that there's quite a bit of difference there. Look at the linear function here, moving on at that constant rate. You can see that it's a solid straight line because every time we go right one, we go up the same amount. And that gets that constant rate of change. And you can see that the further they go, the farther they get apart. Let's zoom in. For a bit or a small section, they look very similar. So, and that's okay. We should still be able to differentiate between the two on a whole, understanding that the exponential function continues to grow faster and faster each time it goes up, growing exponentially, where the linear function grows constantly. So we should be able to find the difference between those two, but you can see that they're pretty much the exact, I'm going to say opposite, but you get the idea. So that should take care of most of our notes for today. Let me blow this up, make sure that there's nothing else I need to say inside these notes here. Again, we pulled in absolute value, showed that how the vertex form works with absolute value, that's similar to our exponential function. We talked about the growth factor, the initial value, and what x means to this, again, as in events. We showed the differences, meaning how to identify between a linear function using differences and finding the common ratio with exponential functions, again, up here at the top. So we've covered quite a bit of material. I think that you guys have a good, nice overview of exponential functions. Don't think that you should have a solid understanding of it yet. This was an introduction to get you to some of the concepts. So with that being said and done, I think these videos gotten long enough, and I will see you in class to fill in anything else that we need to talk about. All right, have a good night.